Hey, space enthusiasts! Ever wondered about the most mysterious objects in the universe? Today, we're talking about black holes. These aren't just empty spaces, they are regions of extreme gravity so strong that nothing, not even light, can escape them. But here's the real head-scratcher. Did you know that black holes also mess with time? It's true. Time itself acts weird near these cosmic giants. Join me on this episode of Time Pilgrimage as we explore the mind-bending question, do black holes warp time itself? Let's find out. Our journey begins with Albert Einstein. His theory of relativity changed how we see the universe, especially how gravity and time work together. Imagine a trampoline. If you put a bowling ball in the middle, it creates a dip, right? Now roll a tennis ball across, it won't go in a straight line. The bowling ball's weight curves its path. That's kind of how gravity works. Massive objects like black holes create a dip in space-time, bending the path of anything that comes near them, including light itself. But here's the even wilder part. Einstein also predicted that gravity doesn't just warp space, it warps time too, and the stronger the gravity, the slower time ticks. So, how slow does time get near a black hole? Let's find out. We often think of time as a straight line ticking away at a constant pace. But what if I told you that's not entirely true? Imagine time as a river flowing through the universe. In some places the river flows smoothly and evenly. But near massive objects like black holes, the river gets turbulent, it speeds up and slows down, creating whirlpools and eddies. That's because gravity doesn't just pull on matter, it pulls on time itself. The stronger the gravity, the more it stretches and distorts the fabric of time. This phenomenon, known as time dilation, is one of the most mind-boggling predictions of Einstein's theory of relativity. It means that time passes differently depending on where you are and how strong the gravitational field is around you. Let's go back to our trampoline analogy. Remember how the bowling ball created a dip, representing the curvature of space-time caused by gravity? Now imagine placing a clock at different points on the trampoline. The clock closest to the bowling ball, where gravity is strongest, would tick slower than a clock farther away. That's because time itself is being stretched and slowed down by the intense gravitational pull. This isn't just a theoretical concept, it's been experimentally proven. Atomic clocks, incredibly precise timekeepers, have shown that time moves slightly slower at sea level, where gravity is stronger, compared to higher altitudes. Now, imagine the extreme gravity of a black hole. The closer you get to a black hole, the slower time would run for you compared to someone observing from a safe distance. At the very edge of a black hole lies a boundary known as the event horizon, a point of no return. Once something crosses the event horizon, not even light can escape the black hole's gravitational pull. Now, here's where things get really weird. As you approach the event horizon of a black hole, time dilation becomes increasingly extreme. To an outside observer, it would appear as if you were moving slower and slower, your clock ticking slower and slower, until you eventually froze in time at the event horizon. From your perspective, however, time would seem to flow normally as you fell into the black hole. You wouldn't notice anything unusual about time itself. Of course, you'd have other things to worry about, like the intense gravitational forces tearing you apart. But the point is, time is relative. It's not a universal constant, it's a fluid concept that's influenced by gravity. And nowhere is this more apparent than near the mind-boggling objects we call black holes. Let's conduct a thought experiment. Imagine you're an astronaut on a mission to study a black hole up close. You're approaching the event horizon. Light from stars behind the black hole bends and distorts, creating a halo-like effect. This is gravitational lensing. You cautiously approach the event horizon. Time ticks slower for you compared to Earth. Crossing the event horizon, time would stop for you. To understand why this happens, we need to shift our perspective on time. Instead of thinking of time as a straight line, imagine it as a fourth dimension, along with the three dimensions of space we're familiar with: length, width, and height. Just as a ball curves a rubber sheet, representing the fabric of space, a black hole's immense gravity curves the fabric of space-time, creating a deep, gravitational well. This curvature is what causes time to slow down near a black hole. It's like trying to walk straight across a hill. The steeper the hill, or the stronger the gravity, the more your path is curved, and the longer it takes to reach your destination. So, time itself is not flowing at a constant rate everywhere in the universe, it's being stretched and compressed by gravity, depending on the mass of nearby objects. This interconnectedness of space and time is a fundamental concept in Einstein's theory of relativity. It tells us that space and time are not separate entities but rather two sides of the same coin. woven together into a seamless fabric that permeates the universe. And just like any fabric, space-time can be bent, stretched, and warped by the presence of mass and energy. The more massive an object, the greater its gravitational pull and the more it distorts the fabric of space-time around it. Black holes, being the densest objects in the universe, represent the most extreme examples of this warping effect. Their gravitational pull is so strong that it creates a singularity at their center, a point where space-time itself breaks down. What happens inside a black hole, beyond the event horizon, remains one of the biggest mysteries in modern physics. Some theories suggest that black holes could be gateways to other universes or dimensions, while others propose that they might lead to the end of time as we know it. However, these ideas are still highly speculative. The extreme conditions inside black holes make it incredibly difficult to study them directly, and our current understanding of physics breaks down at the singularity. Despite these challenges, scientists are constantly working to unravel the mysteries of black holes. By studying the behavior of matter and radiation around these cosmic giants, we can gain valuable insights into the nature of gravity, time, and the universe itself. So while we may never be able to journey into a black hole and experience time dilation firsthand, the study of these enigmatic objects continues to push the boundaries of our understanding and ignite our imaginations. While the concept of time warping near black holes might seem like science fiction, there's growing evidence to support it. One compelling piece of evidence comes from observing the behavior of matter as it falls into a black hole. As gas and dust spiral toward the event horizon, they heat up to incredible temperatures, emitting intense X-rays. These X-rays can be detected by telescopes here on Earth, providing us with a glimpse of the extreme environment around a black hole. But here's the interesting part. Scientists have observed that these X-ray emissions sometimes echo or reverberate, as if they're being reflected off something close to the event horizon. These light echoes suggest that the region around a black hole is distorted, with light taking longer to escape due to the strong gravitational pull. This is consistent with the predictions of time dilation, where time slows down near a massive object. Another intriguing piece of evidence comes from studying binary systems where a pulsar orbits a black hole. Pulsars are rapidly rotating neutron stars that emit beams of radiation, like cosmic lighthouses. When a pulsar is in a binary system with a black hole, its orbital period, the time it takes to complete one orbit, can be affected by the black hole's gravity. Scientists have observed binary systems where the pulsar's orbital period is slightly longer than expected, suggesting that time is being stretched and distorted by the black hole's gravity. These observations provide further support for Einstein's theory of general relativity and its predictions about the strange and wonderful ways that gravity influences time. On a grander scale, astronomers are also studying the role of supermassive black holes in galaxy evolution. These colossal black holes, millions or even billions of times the mass of our Sun, reside at the centers of most galaxies, including our own Milky Way. When galaxies collide and merge, a common occurrence in the universe, their central black holes can interact in dramatic ways. As these black holes spiral toward each other, they create gravitational waves, ripples in the fabric of space-time that propagate outward at the speed of light. These gravitational waves carry energy away from the system, causing the black holes to spiral closer and closer together until they eventually merge into a single, even more massive black hole. The detection of gravitational waves in 2015, from the merger of two black holes billions of light-years away, was a groundbreaking achievement, confirming a key prediction of Einstein's theory and ushering in a new era of gravitational wave astronomy. As we continue to explore the universe with increasingly sophisticated telescopes and observatories, we're likely to uncover even more mind-bending phenomena related to black holes and their effects on time and space. One exciting area of research is the study of wormholes, theoretical tunnels that could connect different points in space-time, potentially allowing for faster-than-light travel or even time travel. While wormholes remain highly speculative, the possibility of their existence is a testament to the incredible strangeness of the universe as we understand it. The study of black holes is a journey into the most extreme and mysterious realms of the cosmos, pushing the boundaries of our understanding and challenging us to rethink the very nature of reality itself. The idea of time travel has captivated humanity for centuries, but could black holes, with their mind-bending effects on time, hold the key to unlocking this elusive dream? While traveling backward in time remains highly speculative, Some physicists believe that black holes could potentially act as one-way time machines to the future. Remember how time slows down near a massive object? If you were to orbit a black hole at a safe distance, time would pass slower for you compared to someone on Earth. You could spend a few years in close proximity to the black hole, and when you return to Earth, decades or even centuries might have passed. This concept, known as gravitational time dilation, is a real phenomenon predicted by Einstein's theory of relativity. However, building a practical time machine based on this principle would require overcoming immense technological and engineering challenges. To further illustrate the mind-boggling nature of time dilation near black holes, let's revisit a classic thought experiment in relativity, the twin paradox. Imagine two identical twins. One twin stays on Earth, while the other embarks on a high-speed journey into space at a significant fraction of the speed of light. According to special relativity, the twin traveling at high speed will age slower than the twin who remained on Earth. Now, let's introduce a black hole into the equation. Instead of traveling at high speed, imagine one twin spends a considerable amount of time orbiting a black hole at a safe distance, while the other twin remains on Earth. When the spacefaring twin returns to Earth, they would have aged significantly less than their Earthbound sibling, even more so than if they had traveled at high speed in the absence of a black hole. The extreme gravity of the black hole amplifies the time dilation effect, making the age difference between the twins even greater. What happens to information that falls into black holes? Classical physics says information is never destroyed, but black holes seem to violate this principle. Once something crosses the event horizon, it's gone forever. This leads to the black hole information paradox. Some theories suggest information is encoded on the event horizon or released through Hawking radiation. At the heart of every black hole lies a point of infinite density and zero volume, known as the singularity. Here, the known laws of physics break down and our current understanding of space, time, and gravity completely collapses. What happens at the singularity is anyone's guess. Some theories speculate that it might be a point where space and time cease to exist as we know them, perhaps connecting to other universes or dimensions. Others suggest that quantum effects might prevent the singularity from forming in the first place, leading to a more complex and nuanced picture of the inner workings of black holes. The singularity represents the ultimate frontier of our knowledge, a place where the boundaries of science and imagination blur, leaving us with more questions than answers. Black holes warp space and time itself. They slow down clocks and offer glimpses into the future. Einstein's theory helps us understand these bizarre objects. We've seen time warping through X-ray echoes and gravitational waves. Time is a fluid, dynamic entity influenced by space. Black holes serve as cosmic laboratories, probing our understanding of time. We open ourselves to a universe far stranger and more wondrous than we ever imagined. What are your thoughts on these cosmic timekeepers and their mind-bending effects? Do you think we'll ever unlock the secrets of time travel or understand what lies beyond the event horizon? Share your thoughts and theories in the comments below. Let's keep the conversation going. Thank you for watching Time Pilgrimage, and as always, please remember to subscribe and like. If there is a topic that you would like to explore, please drop a comment. Until next time, keep looking up and never stop questioning the universe around us.